All right, last lecture before the midterm. Our reviews on Tuesday. And today we're going to talk about something that will seem familiar to folks who have taken Comp 220 algorithms. If you have not taken Comp 220 algorithms, this will be a good little introduction to some abstract data types and data structures that we'll talk about at that point. So it's kind of a dual purpose lecture. And also it introduces just some other ways of using classes. We'll talk a little bit about what it means to have a base class versus, the classes that we've been introduced so far. Same announcements as last time. We have our map of instances lab. That's due Friday. Also, we have today one a little bit trickier called a Fibonacci sequence. We're going to use a queue and a stack. This is kind of a known algorithm to build a Fibonacci sequence. So these are two of the containers we're going to study today, queue and stack. So this is just one of many algorithms you can use them for. And if you take Comp 220, some of you may remember some algorithms where you used queues and stacks in some interesting ways. They're really foundational tools for solving very large problems. So they're just always around when we're doing computer science. So next week you have quiz 4. It's available now. It's just no due date. You'll have 3 tries. It covers these 2 lectures, so it's a good review lecture. And then we'll have our midterm practice probably tomorrow by noon. I'm going to get up tomorrow morning and go over it one more time. And that'll give you a very good sense of what's coming next week. I don't think it'll blow anybody up, especially since it's an open book test. So if you've been kind of following along, you should feel okay with that. And the review for lecture 15 is kind of monstrous right now. So if you look at it, don't let it throw you. I will probably be paring that back and coming up with a strategy to, pick and choose. But if you want one place to go to just sort of look at everything all in one set of slides, lecture 15 will have it. It's currently at like 100 slides, which is kind of insane. So I'm not going to make anybody sit through that next Tuesday. I'll try to find a better way to kind of represent that to you. And I'll release the Zoom video early because, again, I know it's kind of a busy time before the spring break. So folks this weekend should be able to watch last year's review video or previous years if you want to. It's pretty exhausting, but it's there if you kind of want to take advantage of it. And then we'll have our midterm on Thursday. So don't forget that. Maybe set your time for that and make sure that you're in and comfortable by the time our time starts. Okay. Now, Tuesday after spring break, we have our homework for blackjack. So I know it's hard to find time to work on that now, but it's if you do a little bit on it, you might find that you'll make some good progress in the time that you have. Let me pause there for a moment. I'll put this up so you can kind of review that, but I'll close our door here so we don't bother our neighbors. 1 second. Okay, so same stuff as last time, so I won't go through this, but let me know if you have any questions, and we'll talk more about this on Tuesday of next week. Today, we want to talk about something called container adapters. We'll do a quick review on pairs and maps, which we looked at last time. But container adapters are called adapters because they take advantage of the things we already know about. They sort of simplify them by putting a wrapper around them, sort of like a reskinning of a game or, a wrapper or mask on top of something. They really are some of the classes we already know, but they change what the methods are and they change what the class is called. And that's why we call them adapters. So they simplify the access and they prevent us maybe from doing things that would slow down performance. So usually taking things away is a better way of controlling how people might or limiting how people might misuse these classes. So they're called stack, queue, and priority queue. And in algorithms, we refer to these as an abstract data type. It's an idea. All of us have been to maybe one of those places where we stack the dishes up and then we take the dishes off the top as we need them. That's called a stack. It's not a surprising concept, but they are fairly ubiquitous in software, especially at low levels. We use stacks all the time. Queues we'll see here as an example. is really just lining up for food. So like if you line up to go into a restaurant, whoever gets in line first gets served first. So we call that first in, first out, or FIFO. So a stack is something we call a FIFO data type. And a queue, or a stack, sorry, a stack is a LIFO, last in, first out. Whichever plate we put in last, that's the plate we take off the top. So these are two really, really common, honestly, low-level things that exist almost in every device that we use. There's another one that's super powerful called a priority queue. It's more like bubbles. It's like whatever is the most important bubble floats to the top. And we really don't care so much about the bubbles that are floating down below. They don't need to be sorted. We just, whenever we want the most important bubble, we want that thing to be handed over to us. So that's sort of a partially sorted data structure, and one that some of you might remember we talked about in Comp 220. So a lot of these things should be a little familiar to you. But just a little syntax to wake up our brains. Last time we talked about this sort of low-level class called a pair. It's a templated class. It's got two things we get to put in there, and then we can call our constructor and hand in those two things to create it. And when we access the members of it, they're not getters and setters. They're actually public data members of the class. So we literally say my pair.first and my pair.second. And you can put anything in there. You can put pointers in there. You can put floats in there. You can put instances of an entire class in there. And so it's really quite a fundamental workhorse for C++. And we'll see that we use that inside of most of our associative containers like maps and unordered maps, and the various types that we had. Last time we said, hey, these are key value pairs. Usually the key is something we look up, and it might be unique or it might not be unique. But if we're using a normal map, they're going to be unique. We're not allowed to have duplicates like a dictionary or a social security lookup thing. And the really key thing is they're fast. So if I had 1,000,000 of these key value pairs, I can pull these things out in what we call constant time, right? So we can find ways, well, depending on whether they're ordered or not, we can pull these things out very fast, at least a lot faster than searching linearly through a vector. So there's a lot going on underneath the surface of these maps. And that's something that we learn about in algorithms if you have not already taken that class. Okay. So keys and values, and in a lot of ways, this is a database, right? So a lot of databases out there are key value pair databases, and we actually can just pull things up if we know what we're looking for. Okay. Inside of C++, they're containers and they have iterators. So we can create them this way, right? We give the specification of the pair, key and value. That doesn't have anything in it yet, but of course, we can then go ahead and insert things into there. And we can either insert a pair like in a very detailed way, or we can let C++ figure it out. We can say, hey, you figure it out. Here's one thing and there's another thing, that's a pair. And it will kind of like pouring water on a sponge. It will convert that thing into an actual pair because it knows it's a map. It's like, oh, you need a map pair right there that matches the string int. Okay. So the safest way to tell whether there's an apple in this my map is to say if mymap.count apple is greater than 0, then I can go ahead and print it out. Otherwise, you might accidentally create an apple and not even really realize you've done it. Okay, so that's a real thing you got to watch out for. And if there's not one in there, well, then we don't want to try to access it, of course. So that is the safest way to access things from inside of there. Also, for these default maps, there's self-sorting, which is pretty cool. They are binary search trees underneath, for those of you who remember Comp 220. And we can override the default sorting by putting a functional object in there. We'll talk about more of those later in the semester. But that little piece of code lets us change whether they're sorted ascending or descending. Okay. And then looking at more complex code, which we are most certainly going to do in our Blackjack now that's coming up and other ones, we're going to see more and more that we have to really kind of step back and think, wait, what am I doing here? I'm inserting something into this map. with the string and a person. So what is this stuff over here? Well, looks like this is a string and this is maybe sufficient for a person constructor. So this whole thing is sort of a pair that combines the string and the person. But we wouldn't know that if we didn't look at the data type of that particular declaration for my map. But that works, and that's a pretty elegant and common thing to do, is to say, hey, I'm just going to throw those things in there and let C++ figure it out. Okay. So in a set, and now I'm switching gears here back to set, notice I'm just putting in a string if it's a string set. So the pair thing is specific to the map, right? So sets, we didn't really see that before, okay? So here's me creating an instance of a person, right? And it is calling the default constructor to create that person instance. Notice no empty parentheses there. But I could also do something like this. Okay, P already exists, so I just want you to assign curly braces Jeff Yates. Well, that is going to, again, similar to up here, automatically create a person instance by looking at the P and going, oh, okay, that's a person, so I guess I better make a person, and then we'll copy it over, okay? So these are really handy, but there's a lot of magic going on there. Here, when we say hand one card, well, this curly brace here is going to create a hand of cards. But you have to look at the prototype for homework 4 to see, oh, that constructor is looking for a vector of integers. So this is just one integer. I could put 100 integers in there that represent the IDs of a collection of cards, maybe a whole deck of cards, or maybe I'm just holding 5 cards in a poker game. So what does that curly brace pair mean? We got to look at the definition of hand and look at its constructor to find out, okay? Now, blackjack is a little more complicated. So the blackjack constructor, so I'm just sort of listing the prototype here. Notice that the first argument is the names of the players. And if you don't give me that first argument, then I am going to automatically construct a vector of strings. So that's what that is there. Those are the players in the game. Player and dealer in blackjack is kind of a standard situation in blackjack. So if we don't say it's like, Jim versus Tim, then we're going to see player versus dealer automatically there, okay? Similarly, if we don't provide a vector of IDs, then we're actually not going to have a deck of cards to start with. We're going to have an empty deck, okay? So just a little more time spent on this because I know it's always a little cryptic when you see those things, okay? So it is going to happen probably more and more where we'll just sort of use those curly braces to keep things simple in our code. So there's one construction, there's another construction, there's another one there, etc. Okay. Okay, so on to our topic for today. So ordered and unordered set. So this is just a little side trip to clean up stuff we haven't done. So if you pound include on an unordered set or an unordered map, we're kind of moving away from the world of binary trees. Again, for algorithms folks, we're going to hash tables, which is a very much more optimized storage and access system, but we can't get things in any sorted order. So unordered sets and maps basically mean we're using a hash table or a hashing algorithm. Some of you might remember that. It's pretty cool. It's really good for very large collections where we don't need to sort things in order. It's just like, hey, does somebody in the United States have phone number, blah, 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 right? There should only be one phone number that's unique in the whole United States. So we should be able to just look that up. Does it exist or doesn't it? So hash tables are really good and very fast for that, but I'd never be able to say, oh, give me a list of phone numbers that are a little bit similar to mine, right? A hash table is not good for that. So we get to choose whether we want an unordered or an ordered map or an unordered set or an ordered set or an ordered map, right? So we're going to be looking at the unordered ones for today. Now, separately, we won't go into this because it's just too much, make you all crazy. We could have a multi-set unordered and a multi-map unordered, but we're not going to really explore that permutation. That's there for you if you really want to do that, but we'll just do a little bit with the unordered stuff today. Okay. But all these things have container iterators and size and empties, so they're pretty familiar once you get to know one of them. So let's just compare. Here's our ordered set. We saw this last time. Here's a bunch of numbers that are going to go into the set, and they're going to automatically order themselves. So if I insert a -1 and then I iterate using my range-based iterator, I'm going to see the -1 come out first because sets automatically create this ordering. And underneath that, there's something like a binary tree under there. If we have an unordered set, which is the data type unordered underscore set, and I do the exact same stuff and I insert -1, it is unspecified. Every compiler can choose any order that it wants for that stuff to come out because unordered sets don't have to be in order. So if we kind of go through every one of them, there's no guarantee of what order they're going to actually be in. On one compiler or one computer, it might be one way. Another compiler, another computer might be another way. Okay. So we're really more interested in, does it exist? Not so much like what's the order if we decide to use something like that. And the same is true for, so for insertion of that, right? Still, these are still unique keys, right? If I try to insert 11 twice, it's not going to do anything because 11's already in there, right? I've already inserted it there. So I'm still going to get rejected, okay? If I put a -1 in there and I print it out, we'll get some values in some order, right? So let's just do this for a quick warm up. We probably wouldn't use a set to calculate an average, right? Because it's not going to let us have duplicates. But let's just go ahead and try this real quick. You can look at it if you want and come back. But remember to include, include the unordered set, right? So we're going to load that up. We're going to open our file. And we got to work with Program, IZPro, or Replit to get our data file here, right? So we'll read in all the values and we'll use our range-based for loop and then calculate an average real quick, okay? So feel free to jump into this one. I'm going to kind of fly over this because it's kind of basic, but it's kind of, it's good to see how we get this stuff off the ground, where you do an unordered set of int, so UO set, we load in each item, which is going to be an integer from our file, right? Close the file, and then we'll go through using the range-based for loop and print them out, okay? And then we can go through again if we want and just sum them up, okay? So nothing too magical about iterating through these. And we just have to remember that if we're going to calculate the average, we probably want to change the sum to a float, right? So we were just going through this in my intro class today. This should probably be a float if we want a really accurate average. What I've done here is probably not very accurate. But this is just basic access to that particular data type, okay? Now, we probably use a vector for this. The reason we would use a set is for like phone numbers or something like that that are unique, that we just want to look up really fast. So this is not a really great example of what to do here, or how, of choosing the right container type. But let's take a look at maps, right? So here's a map with a character, key, and an integer value. That's like the backpack of data. And the character is what we use to look something up. So we could put a letter and a value in there if we wanted to, right? We could also, instead of calling out the pair explicitly, use our curly brace format like we saw earlier today, right? Okay. So everything with the unordered map is pretty similar to the ordered map. It's just that we can't pull out things in any specific sorted order, okay? So let's take a look at this one real quick. And this one is really kind of interesting. So I'll spend a little more time on this. But if these things are supposed to be faster, how do we prove it to ourselves, right? So a lot of times, we take it for granted. Somebody says, oh, yeah, unordered is faster because it's a hash table. Well, let's find out, right? So let's load up a bunch of values and see how much faster it is to load up a lot of values. The ordered map is a binary tree insertion. And again, for algorithms folks, we talk about that being log of n. So if I got a million things, it's going to be whatever the log base 2 of a million is. versus a hash table, which should never take longer no matter how many things are in it, which almost seems magical. So, but what's going to happen in reality? So let's take a look at actually doing this one. And what we're going to use is this high resolution clock that measures the time that that occurs between operations. So we'll kind of set a start marker, and then later on we'll have a stop marker, and then we'll kind of do that again for a map, right? We'll have an unordered map, right? And then we'll have an ordered map, and we'll measure those two values, okay? So we're going to need two variables for this. So let me see if we can work through this one real quick without it getting super, super, super long. Okay. Oh, it's going to make me sign up. Okay. Okay. Well, let's do it down here. Okay. Okay. Getting better at that. Okay, so this is kind of cool to see in action. You don't have to do it, but you might want to see the results of this. So what we're going to do here is we're going to open up a file. We've got a regular map here, and we're going to start our clock, and then we're going to say, while I can read stuff, add that thing to the map. So this is our really concise trick for saying, put a word in there, and if it was 0, increment to 1, and if it was already there, add 1 to whatever was already there, okay? So that's a very, very concise way to add something to a map if you know what you're doing. And then we'll stop, right? And then down below, right, and we'll kind of measure that duration down here, right, and print what that is. So to do that with a really small file, it's only going to take a few seconds. Oh, looks like I got a warning in there for how I did that. Oh, I think I need to run this one over there and not barred. No, interesting. Huh. Okay. I wonder if I corrupted my file. Oh, it looks like I corrupted my file. Let me undo something. Maybe I hit a key accident. There we go. Okay. I modified that unintentionally. So I read 6 words, took 36 microseconds, but if I change this over to barred.txt, that's our big Shakespeare file. So that's going to take a little bit longer to load all of those words in. So that's 188 words. It's got to be done a lot more than that, unless, again, oh, I corrupted my file. So it looks like this undo bug has kind of bitten us for our barred file. Okay, so that is really disappointing. Okay, I'll have to come back to that. Let me cut to the chase then, sorry, on the resolution. So if we do all of that code a second time for a duration 2, what we find out is our unordered map is more than 2 times faster than our ordered map. So we can kind of prove that this hash table thing is actually pretty fast for insertion. And if we went searching for stuff, we'd see that it's also very fast for that as well. So it's definitely faster if you don't need to sort your data to go with a data structure that, doesn't really care about that kind of thing, okay? So a little bit maybe over some of our heads if we haven't done Comp 220 yet, but hopefully for those of you who have, kind of rings a bell, reminds you a little bit of some of the choices that we were able to make before, okay? So those are unordered and ordered. And now we're going to kind of leave those behind and talk about this idea of container adapters for stacks and queues and priority queues. So let's talk about what we mean by an adapter first. So Vector, for example, has all the things we need to simulate a stack. So if you remember when we first started making a deck of cards in our one lecture, we had like a list for a deck of cards and a vector for a deck of cards. So we could do it with all these different classes. So what the good people at C++ did for us was say, hey, we're just going to sort of take these things and wrap something around it and call it something new. So in this particular case, that is what we'd say is vector is a base class for the stack. we don't see it and we don't know it because it's sort of hiding underneath the stack wrapper, okay? And so we'll learn how to do this ourselves when we create derived classes. But here, our stack is essentially going to be derived from one of our base containers. Same with the queue and same with the priority queue, okay? And so they allow us to just sort of use that thing in a much more efficient way. And incidentally, STL stands for Standard Template Library. It's sort of a collection of libraries. It's kind of an old word. We don't use it as much. We use STDs sometimes now. But if you see me using that, that's what that's referring to. But let's talk about our stack. So if you include stack library, now we have this capability where we can push things like those plates, in a restaurant or something, right? So we call that pushing, right? And if I pop something off, of course, it's just going to take the thing off the top. So these are methods, and stacks do not let us just sort of access them in any way we want. They're only going to let us see what's on top. So I can't really see what's in a stack unless I take the stack apart, okay? And so the advantage of that is, in theory, that things go a lot faster. We're not letting you have iterators where you can walk through all of those. So underneath, they've sort of implemented it, I guess, in some pretty efficient way, right? So this idea of pushing and popping is pretty familiar, I think. So these are our methods, push and pop. Top is a way of peeking at what's on the top without actually taking it off. So I can see what's on the top of the stack and even potentially change what's on the top of the stack. I can ask whether the stack is empty. I can ask how many things are in the stack, but that's about it. And then I can like swap two stacks, stack A dot swap stack B. But otherwise it's super simplified, okay? So if you look at all of the methods in gray that all of the containers support, we don't really allow that much stuff to be used. Push, pop, in place, we don't really go into, but you can kind of see they're all fairly simplified here, okay? And that's a good thing. Just makes it easier to kind of work with, okay? So let's take a look at the actual code. Here's a stack, right? And here's the first kind of surprise. This is not supported. I can't do that. Right? I can't start out life and say, oh, by the way, I want my stack to have 3, 4, 5, 6 in it. Stacks can't be initialized that way. We literally have to execute a loop. So I could say for auto item in this package of numbers, which probably gets turned into a vector or something, right? Push each item, push the 3, then the 4, then the 5, then the 6, okay? So that's okay. That's a kind of a shortcut for filling my stack up. And then if I push another thing, of course, that's going to go on top, okay? So if I peek at that, we can see that that's the 10, right? Now, the thing to watch out for is pop does not return something. So if I say, cout s.pop, some languages support that, but C++ does not. So you'll probably find out from the compiler that you're trying to print a void or something like that. So we got a peek and then pop, basically, in the C++ containers, okay? So this is all the vector methods, just to, look at, what's underneath all of this, right? Probably it's a vector. We don't know for sure that it's a vector, but it could be a vector or something similar to it, right? And so we could adapt and hide a lot of these things and rename them by using the vector as a base class. So we won't go into that right now, but just kind of let you know, these are the things that could be our push and pop and top if we really wanted to do that, okay? We would just have to come up with a different wrapper or name for those things and then hide everything else, okay? Now, stacks do not have iterators, so the iterators have been removed. And so we can't, again, we cannot print out a stack unless we make a copy of the stack and then destroy it. So here's how we would have to make a copy is say stack of some type TMP, and then while TMP is not empty, print out the top and pop it. Okay, so we have to literally destroy it in order to print it. So we need to make a copy of it first and then we can kind of iterate through it and see what's inside. Most of the time, we don't need to do this. But since we're just learning, we'll write some functions to help us visualize the stack while we're working on it, okay? So, but there are no iterators or range-based for loops that will allow us to walk through that stack, okay? So let's take a look at some interesting aspects of the stack. So if I do this, right, for auto ampersand item 3456, it's going to push them in the stack this way, okay? So one of the behaviors of the stack that's sort of obvious is it's a handy way of reversing things. You push stuff into the stack, and when you pop it out, you're basically popping it out in reverse order, okay? So if I print this thing out the way I, popped it out, it's sort of the reverse of the way, it is the reverse of the way I pushed it in, okay? So stacks are really used a lot of the times when you got a bunch of things that you need to reverse. You take it out of wherever it was, you put it in the stack, and then you pop it back out again, and that's your reversal. So a lot of basic algorithms will use a stack in that way. And our lab today will kind of do that as well, okay? So that is the reverse of our original pushing order. So we see that when we print that thing out, okay? So we iterate 3, 4, 5, 6, and then we pop out in reverse, okay? So let's just try this one. I think this one's easy enough. We can do this. If the value the user wants is greater than 0, push it. Otherwise, pop it. Otherwise, quit the program, okay? So let's take a look at the code here together. Whoa, that's really bright. Ooh. Okay, so we'll say, okay, let's check our libraries. So we've got our stack, that's good. So we're gonna say, create a real stack. So we're gonna say stack int s for stack, okay? And then I'm gonna say if number equals 0, break, otherwise, else if num is greater than 0, then s dot push num, okay? I got that backwards. I'll just do this way. Else if num is less than 0, s dot pop, okay? No, all right, just pop, right? I need to say pop num, okay? Now, if I want to at any time know what my stack looks like, I'm going to have to copy it into something. So we'll say stack int int temp, okay? And I will say while stack is not empty, print its top, right? But I'm going to copy in from my S stack. So that copies the entire stack. And now I can go ahead and do my while loop. So I'll just say while temp not temp while not temp dot empty, okay? Cout temp dot top and temp dot pop, okay, like that, okay? And I'll put a comma in there so they don't all jam up at the same time, okay? Yeah, I had a feeling I wasn't gonna get away with it. Perfect. There we go. Okay, so just say 1, 2, 3, 4, 5. So notice we're printing every time. So 1 goes in first, so that's the bottom of the stack, right? 2 is the top. It's kind of hard to print stacks on the screen because they want to be vertical, but we have to do them sort of side to side, okay? So we're deconstructing our stack, which kind of reverses it. And so we're printing from, top to bottom, basically, okay, as we're deconstructing our stack. So if I want to pop something, -1, now I have the 4, -1, -1, okay? Now I didn't put any emergency checks, so I'm probably going to crash here if I try to go too far, although maybe my while loop will execute. And yeah, there we go. Yeah, so I should have had something like a while loop that said while not empty up here, etc. Okay. So, but there's your basic stack axis. Okay. And there's our code. Okay. So stacks are kind of fun. They're easy to understand, easy to relate to. They do some interesting things. Okay. Now let's contrast that with queues. Queues are like that restaurant thing. It's like you want to go get some food at your favorite food truck or restaurant or whatever. So when we push into a queue, we kind of all go all the way to the front, assuming the queue is empty, and wait to be served, right? So we're pushing, pushing, pushing. So we use the word NQ. So NQ is like a verb. We NQ something. We push it in, and it's going to slide all the way to the right. Now in this class, I kind of tend to draw queues as going from left to right. We could have done it the other way around. There's no real, right or wrong. But the front of the queue is where the person who's been waiting the longest sits, okay? So the oldest thing in the queue is at the front, and the newest thing in the queue is at the back of the queue, okay? And we push at the back and pop from the front, which is different than our stack, okay? So every time we pop something, you can think about, serving someone their restaurant. And in fact, when we do our multi-threaded restaurant simulation at the end of the semester, we'll use a lot of pushing and popping like this, okay? So here's our queue creation, really simple, right? Similarly, not supported. We can't just create it with an initial thing in there. We got to do the pushing. So we could fill up our queue this way, 3, 4, 5, 6. So stop and imagine for a moment where the 3 is. All right, I have an empty queue and NQ the 3, and it slides to the right, then the 4, then the 5, right? So that's just our notation, okay? So I can always peek at the front, which is at the right, the way we're drawing it, or you could just think about it as being the oldest thing that's in the queue. And then I can pop the oldest thing, okay? But again, it's not going to return anything, okay? It's just going to pop that thing off of there. But in this case now, unlike the stack, I can also see what's at the back or on the left side. So I can't pop from the left because that's not what a queue does. So I can only just peek and see, well, what did I just put in? What's the newest thing in the queue? It's kind of the person waiting at the back of the line, okay? So sometimes the front of the line, back of the line thing helps because you think of it like that, like restaurant line, right? So we've got just a few methods, not many. And although these are references, as soon as you assign them to something, it ends up being a copy. So there are some tricky bugs in here. You can change it while it's on the queue via the reference, but as soon as you assign it to something, it's no longer the thing that was in the queue. So that's a really interesting problem, okay? So when you pop something off a queue, really, you're getting a copy of it. So does it matter whether that's an exact copy or not? If the original was destroyed, it's sort of a, an interesting question. We'll come back to that, but empty, all the other normal things we can do, pretty straightforward with queue, okay? And in place, just some extra stuff we're not going to go into this semester. Okay. And again, no iterators. We can't go through them to inspect them. All we can do, once again, is make a copy. And then while that temp copy is not empty, pop from the front, print and pop, right? Print and pop. Okay. Which is not something we usually do, right? Usually we just leave those things alone and just take what's next in the queue. We don't normally try to print the whole thing out every time we change it. It's not a normal thing you do with the queue. Okay. So let's try to follow through the code. Here's our initialization, right? So we're going to push it, okay? And then while that thing is not empty, we're going to look at the front and pop it, okay? So just think through the process, right? So we put the 3 in. Okay, we're popping from the front, we're pushing from the back. 3, 4, 5, 6. Okay, And first in, first out, again, is a FIFO data structure. So whatever was first in line gets served first. And notice what happens when we're printing. And a lot of confusion enters in because it's like, wait a minute, isn't that reversed? And it's like, well, yeah, it is kind of, because we're printing from left to right, but we're popping, on the right side. So it can be confusing trying to debug your cues sometimes. Just keep in mind that process, right? Okay. So in a sense, when we see out on a, computer left to right, we get that reverse. Yes. When you pop them out, does the size decrease? Yes, it does immediately. Yeah. So you could be checking for a certain size actually. And so in a sense, empty is a synonym for size equals 0 is one way to think of it. Yeah. So let's do this. Let's push and pop into a queue. This is the same structure we saw last time. So it's just, another kind of quick way to get to know this one. Let me check this and make sure everything's working. Pretty sure my link was there. I was checking it earlier. There it is. Okay. A little too much. Okay. So, so we got we're going to create our cube. So it's just going to be QUE int. It's kind of a weird thing, right? That's Q. Okay. And then we'll say if number 0 break, okay. If, let's see, remove from Q. So if num is less than 0, then we'll say Q, oh, sorry, Q dot pop. Okay. But I think we want to print it out. Do we want to print it out? No, we're not going to print it out. And then we'll say if num is greater than 0, right? Less than 0, sorry. Fumbling around with my typing here. Q dot push. No. Okay. Okay. And then when we want to print it out, we need to make a copy. So we'll say QE, UE, int, T, EMP equals Q. Okay. Okay, and we'll say while temp, well, not temp dot empty, do the following. Cout temp dot top. Sorry, front. And then temp dot pop. Okay. Let me add a comma there. I feel like I'm missing something here, but let's see what happens. Okay. I'll get lucky. Okay. 1, 2, 3, 4. Right. So notice, and this is the confusing part, since we got a print from the front of the queue, my front doesn't really match my slides in my code. So notice I have front over here and back over here, which is the reverse of my slides. Thinking back, if I could rewrite all my slides, I'd probably change my restaurant queue to go from left to right, right to left, but that's what it is. So it's a little bit reversed in my code because of the way we print, okay? So the front of the queue has a 1, which is the oldest thing in the queue because that's what I put in first, and then the 2 and the 3 and the 4, okay? Okay, and then we can start removing stuff, okay? Oops. Right, -1, -1, etc. Okay, pretty straightforward, right? Pushing stuff in, popping stuff out. Okay. So again, we're not really usually going to print that queue out like that all the time. That's just kind of what we're doing as a way to visualize things. Now, the really useful thing, and you do see this in algorithms a lot, and we did see this, although it probably went over some of our heads at the time, in Comp 220. We want to reverse a queue. So the way we do that is we pop out of the queue front into a stack, and we re-push it into the queue, right? Until the stack is empty. And now we have inverted the order of our queue. So notice there's 4, 3, 2, 1, right? Now we are 1, 2, 3, 4. So that's a classic thing that we do with a queue and a stack whenever we got to reverse something very, very quickly and elegantly. Okay. Good quiz question there. You'll probably run into some code samples on that. Okay, so let's take a look at this one real quick. So we're going to write a new version of show queue. I always say if you want to get to know somebody else's software, print out their data structures, right? So whenever you print out somebody's data structure in really comprehensive way, it teaches you what the software is doing. And this is almost always something I do if I get dropped into somebody else's code base. It's like, oh, okay, I'm going to start printing out their data structure. So we're going to try to do what this thing is doing, but in reverse. So we're going to create a stack, right? And we're going to do that unpacking thing and then re-queue it, right? And then we'll be able to print out this temporary reversed thing here. So our show queue is going to be pretty inefficient. It's going to just create a brand new stack and a queue so that we can do that reverse thing and print it back out again. Okay. So let's take a look over here at what this actually will do. And if this is program IZ, oh, this is just the online one. Yeah. Okay. So here's our show queue function. Let me see if I can drop that size down just a little bit, right? So if I just copy this thing, okay, like so, like this, copy, right? Oh, it's already started. Ah, okay. So, all right, we can do this. Create an empty stack, right? So we'll just say stack int ts, right? Temp stack. And then we'll say while not queue.empty, empty, right? Like that. There's our closing parenthesis, push copy from the front of the queue into the stack, right? So we're going to say ts.push queue.front, okay? And then we got to get rid of that thing that we just pushed over there. So we're going to say queue.pop, okay? And now we know we get to this point because we've emptied our queue out. So now it's time to unstack. So we'll say queue.push ts.top, okay? And then we can say ts.pop. Okay. And now, if this isn't long enough already, we want to print the queue, right? So we could call show queue here, right? And just pass it the queue. So let's just, let's do that, right? I'm going to just try to speed up the process here. Control /, and I'm going to say show queue, queue. Okay. I think that's the right way to call it, right? Yeah. So let's see if we get lucky and everything works with that. Okay. No. I think I have on line 52, maybe a hit enter. Well, our stack is not empty. Sorry. While not ts dot empty. Okay. I'll take our little comments out of there. Okay. 1, 2, 3, 4. Right. Oh, I didn't call my print queue, so I'm not seeing the results there. Okay. So let's go back to main and show queue reverse. Okay. 1, 2, 3, 4. Oops. We run. Here we go. 1, 2, 3, 4. I missed the 1. But you can kind of see the reverse, right? And the normal. Okay. Just skill building. You know, we don't always want to do that kind of thing. But we could apply some of our template knowledge to make that thing really general so we can show cues of all types without having to write all of that different code. So we can always bring templates to bear on this stuff, but we won't take you through that right now. But it's pretty straightforward, right? All we got to do is just drop that in, change out the data type, right? And we're done. That's all we got to do. And now we have a templated cue printer, okay, for reverse cue. Okay. Okay, so just sort of gymnastics with each of these things. Let's look at our last one, and then we'll get you into the lab here, maybe a little early. Priority queues, super important. We won't go into how they work, but they sort of magically, very quickly float the most important thing to the top. So whenever we pop something, by definition, we're going to get the most important thing. Now, when the most important thing is the largest thing, we call that a maximum priority queue. So this is a maximum priority queue. So you walk into a hospital emergency lobby with, an injury, and it's a bad injury, and you get to the front of the line right away, right? So that's kind of the analogy. So when we push things into a priority queue, they sort of get semi-sorted. They don't go to the top if they're not the most important thing. So when we pop is when we get the most important thing. We don't really know what the order is otherwise. It's kind of hidden from us, right? So when we push, it's sort of like it puts it in sorted order, but it's not really sorting. That would be an expensive operation. It's just sort of creating this. If you've ever had a pile of laundry in the corner of your room or dirty dishes and, but the clean one's on top, it's kind of like that. It's like you don't really pay attention to what's underneath the surface. So that's what a priority queue is. Whenever we push in, it sort of throws stuff around as long as it's not on the top, right? If it's not the most important thing. So as soon as we pop, things shuffle around and we find the next most important thing and the next most important thing. So how that works is more of a question for Comp 220, but it's super easy for us to actually implement this using these containers. Okay, so and for those of you, again, Comp 220, this was a heap array, and we had the bubble up and the bubble down algorithms. So some of you might see that if you take that class. But let's take a look at the code. Priority underscore queue int PQ. And again, can't create it that way. We gotta manually push stuff in there. Okay, so it's going to be pushed in and essentially prioritized when we pop them out. So if I pop now, I'm going to get that 10 back, right? But it's not going to print the 10 or return the 10. I got to do the top kind of peak thing first, pq.top to see what it is, and then pop it off of there. Okay. So we get them in sorted order when we pop them off. So there's something called a heap sort, some of you might remember, which is, hey, if I just push them in the priority queue and then pop them out, it's a way of sorting the information. And so priority queues are a great way of sorting information that's constantly coming at you. If you were on the stock exchange floor and people were giving you orders left and right, and you're like, I'll deal with them when I get a chance, you could be shoving them into a priority queue all the time and then just taking the most important one a moment later. So that's what priority queues actually end up getting used for, sort of real-time processing of things, okay? So we really just have the push and the pop and the top again, and the empty and the size and swaps. So pretty similar to our other adapters as well, okay? So there's not really a top and a bottom, not really. It's just referred to that way by convention in C++, right? They just decided that's how they're going to do it. So we just got to think of it as a top and a bottom thing. Okay. Okay, so let's just look at the code real quick. Same kind of game. I'll let you guys kind of try this one. But rather than me kind of editing it, I'll just show you what's here. Right, so we can read in with the CN and decide whether to push or pop or break, okay? And then copy it over, deconstruct it just so we can prove to ourselves that it's always coming out in sorted order, which it is. And you may ask, well, what is its sorted order? Well, by default, it's going to be ascending sorted order. But what if we wanted to change the sorted order of that, right? So in other words, if that's a max priority queue, how do we change it to automatically prioritize the smallest value? Okay. So we'll take a look at that, right? How do we reverse? Well, we write one of our little functional objects. We create a class, okay? Sort of a quick look back to last week. We create a class that masquerades as a function. We overload the function parameters and we say just return A, whether A is less than B. If I'm given two things, return the Boolean result of the comparison. Okay. So for a max priority queue, we say A less than B. For a min priority queue, we just swap those two. Okay. And then we drop our class name into the third template parameter there for our priority queue. And like that dehydrated sponge, it's going to turn that into an instance and then call it like a function in order to let us control how that sorting order happens. Okay. So again, that's our functional object pattern. Okay. And so we could write those things, right? So let's just take a look at what it takes to write one of those. This is our last one, so we'll get you into lab a little bit early. Let's try to do this one, okay? So what we want to do is create a class that does a comparison between two integers, okay? So it's going to look pretty similar to what we've seen here, okay? So it's just a little bit bigger. So we got our queue. Here's our my compare. So let's take a look at how we got to do this, right? So nobody has to memorize all this stuff. We know we want to overload an operator parenthesis. Okay, so it's been a while since we've written one of these, but let's see if we can do it. So we're not going to write a constructor. We're just going to say, and what are we returning? We're returning a Boolean because that's the answer to our comparison. Bool operator parentheses, because that's our overload, right? And we're going to be given an int A and an int B. We can call them anything we want. And I'm going to return the result of comparing B less than A. I think that was it, right? B less than A, right, for minimum priority queue, okay? So that's the end of my operator overload, right? And I don't need to do anything else. It's got a default constructor by default, right? And so now all the way down here in main, when I create my priority queue, I can just say, hey, I'm going to be using a vector int and a my compare. Now this part is a little bit strange. I have to tell it I'm going to be working with a vector int, and I'm going to give you the comparison function for that, my compare, okay? So this is a class or data type, and this is a class or data type, okay? So the priority queue is going to be using my function. So let's see if we get lucky enough and I didn't make any mistakes. So priority queue, my compare, priority queue from, what did I do wrong here? Show, was it show priority queue? Show priority queue. So it could be, not surprising, I also need to update the type of parameter that I'm using in my argument list, right? So I gotta make everything match. I believe this is how we do that, okay? So that's our show priority queue. I don't think I have any others that I gotta do. Let's see if that does the trick. And that does the trick, right? So 1, 2, 3, 4. So if I pop something off, right, it's going to be the most important thing, which is going to be smaller because I flipped that order around. So I go back and I change that to A less than B, right? Okay. 1, 2, 3, 4. I'm going to show you one more thing here because I think this is, oops, okay, 13, 14, 15, right? So now the biggest thing's on top. But what if I wanted to prioritize odd numbers so they floated to the top? Any guesses how I would do that with my comparator? So I want to return a true if something's odd. Otherwise, I want to return a false. Okay. So I could say, let's see. So it's not really comparing things per se. So, but I could say if A modulo 2 equals 0, then return true. Otherwise, we'll return true, false. So whatever the A is should be the one that gets picked. So let's just see if we get even numbers kind of going to the top. Okay, so I'll say 1, 3, 2, 4. Not really happening for me, is it? That's really interesting. I should have tested that first. 8. Where did my 8 go? Oh, there we go. Okay. So, oh, right. So the odds, I've got it backwards. That's right. So 5, 7, 9. So it is just doing it in the opposite. So the odds are ending up on the top. So I just had to flip my logic around. Okay. So we can do some crazy things here. We're just answering a question and helping it understand which one of these to choose. We don't have to do just a pure comparison. All we got to do is return a Boolean. So I could even say modulo 3, right, and prioritize or deprioritize things that are divisible by 3 evenly. Okay, just kind of silly, but expands our understanding of what's going on there. Okay, so that's our min priority queue, right? Sneaking that little thing inside of there. And with the little caveat that we have to update our show priority queue function as well over there. Okay. Okay. So final questions on any of that stuff before we jump in the lab? Okay. All right. Those are our adapters. So today we're going to try to use a stack and a queue to build a Fibonacci sequence. So this is a Fibonacci sequence. Many of you know 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3. Right? So we're always going to be looking at the previous two things to figure out what the next thing is. And we'll always start our Fibonacci sequence, for this lab at least, with 0 and 1. So we got the first two terms kind of handed to us. So the rest is just how do we kind of come up with a process to do this. So we're going to write a function called getFibStack. And we're going to give a queue to the getFibStack function, and it should return a stack with all of the Fibonacci numbers all the way up to 144. We could go on forever, but we're going to try to just start out with this, right? 1, 0. And then we want to fill up our Fibonacci stack, right? And the way we're going to do it is we're going to take what's at the front of the queue, we're going to put it into the stack. Then we're going to add the front of both of those to the back of the queue. Okay, and then we're going to repeat that sequence. Take the 1 out, put it in the stack, add the front of each, and put it in the back. Okay, take the 1 out, put it in the stack, add the front of each, put it in the back. Okay, so we want to keep going until the top of that thing equals 144. Okay, so it's just a little algorithm that tests our kind of comfort with the code. And it's kind of fun way to actually build a Fibonacci sequence. Okay. So that is it today. And if you need the steps, I won't kind of dwell on this page here because this is just what's in the code. But it's really not too complicated. All the steps are kind of there for you. Okay. But it's the algorithm that we just kind of laid out for you. Okay. And that is that. Right. And so at the end of all that, you should have 144, 89, 55, etc. And you could keep going on forever and ever. Right. But we'll just stop at 144. Okay. So I'll leave you guys with that. And I will be heads up for your email this weekend. Have a great rest. I'll see you guys on Tuesday. Thank you.